Welcome back. Today, let's start looking at macroscopic aspects. And what we're going to do is, we're not going to worry too much about the depth, the rigor, and so on and so forth. Um, uh, I think I also need to mention at this stage, this course is not a math course. Okay, it's not a mathematics course. You need to understand the physical reality far better. We need mathematics to it, so it is a means to an end as far as this course is concerned. So that needs to be clearly kept in mind. Um, so far, we had looked at very rigorous aspects, right, starting right from macroscopic aspects, very basal definitions. Then we built things up. We got a lot of insights. We could use that for design, probably operation, by extending things and so on and so forth. And our basis was a complete picture of the system. And then when we came to turbulent flow and other aspects, we realized that we don't understand things clearly. Okay. However, those are things that are useful. Turbulent flow is very useful. Therefore, we need to be able to handle turbulent flow. We need to design based on turbulent flow and so on. Okay. Some means of starting from a basis was given in the previous lecture. Here, we are going to look at some formulations which are very useful, which may not be based on highly rigorous aspects. There'll be some hand waving somewhere, but they are very useful. Okay. Definitely useful for design and operation. So the remaining part of this chapter is going to look at such aspects. And the first aspect that we are going to look at is called the engineering Bernoulli equation. I'm sure you'd have seen Bernoulli equation in your high school, higher secondary school, or in the early parts of your engineering curriculum. Okay. That probably was a simplistic Bernoulli equation, physics courses and so on. Here, that would have been an ideal Bernoulli equation which does not consider losses. Okay. Delta P by rho plus delta V squared by 2 plus delta G delta Z equals 0, if you recall that. However, this is a practical situation. Ideality doesn't exist. So this is the engineering Bernoulli equation, and we need to understand those non-idealities. Only then can we design devices, processes to overcome those aspects. Fine. Let us see this in some detail. Let me repeat this. It's worthwhile repeating this. Thus far, the understanding of fluid flow was in good depth, but the mathematical effort was significant. We need mathematics, there's no doubt about it. However, this is not a mathematics course. If we can reduce the effort but still get acceptable answers, it may be good for engineering design and operation. And the engineering Bernoulli principle is useful for this purpose. The engineering Bernoulli equation can be derived by starting at the equation of motion. Okay, you start at the equation of motion, momentum balance, you can get to this. Okay. And such a derivation is available in other textbooks, in detailed textbooks. It's the outlines of the derivation are given in your textbook. A more detailed derivation is available in advanced textbooks and papers written on this in the 60s maybe. Okay. In fact, Bird, the first author of the paradigm changing book, Transport Phenomena, he had written a paper on this derivation in the Korean Journal of Chemical Engineering way back in the 1960s. Okay. And I may have mentioned this earlier. I'm very privileged, and I'm happy to tell you that Professor Bird, Professor Robert Bird, he wrote the foreword for your textbook, for my book. The nice story about this, this of course, Transport Phenomena was the book that we all used to look up to. And Bird was one of our rock stars, if you could call it that. And when I wrote this book, but for biological systems with the charge aspects and so on and so forth, Bird's book does not have the charge aspects. When I wrote that, and this book is very thin, it's about 240 pages. Bird's book is thick, about 700, 800 pages. Of course, it's a lot more comprehensive. in terms of whatever it covers. So when I wrote this book of mine, and I thought it will be, or in fact the publisher suggested that it will be good to consider people to write forwards, I said, why not write to Professor Bird himself? Then I wrote to him, I sent him a sample of the book and waited. I think I sent it on a Friday, the email on a Friday. And then, of course, the weekend, Saturday, Sunday, although I was excited, I had to wait. And then Monday came, no response. Tuesday came, no response. Then I said, maybe I've expected too much, expecting Bird to write a foreword was a little too much, and so on, Professor Bird. But Wednesday, I got a response. Wednesday morning, I got a response. It said, this book, Transport Phenomena, was written in 1960, first edition. And Professor Bird, about 10 years ago, was 88 years old, right? And he wrote saying, about 10 years ago, he was 88 years old. And he wrote back saying, the first few lines said, I'm 88 years old, I'm revising my own book with the help of others. Then I said, maybe it's a polite no. And then the next paragraph said, but I like your book, and therefore I'd write a foreword for you. I was very excited that Professor Bird had agreed to write a foreword for my book. And when we were discussing the various aspects, I had to send him the entire book, and he looked through it in 3 days flat. And he even pointed out errors between CP and CV in that book. And that's his level of familiarity, understanding of the material. Okay. And coming back to this, I had derived the engineering Bernoulli equation from a different point of view. He specifically said, don't do that. Don't propagate this method of derivation. It is wrong in a certain sense. I have written a paper on this, and it is in the Korean Journal of Chemical Engineering. And so please don't do that. At least if you give the outlines of the derivation based on the momentum balance equation, that should be fine. And I took his advice. I gave the outlines of the derivation in the textbook, and then he wrote the foreword, which I'm very grateful for. And for this reason, I'm not going to derive the engineering Bernoulli equation in this course. Okay. If you're interested in the outlines, please see the textbook. If you're interested in more detailed aspects, please see the journal article written by Professor Bird in the Korean Journal of Chemical Engineering in the 60s. Here I'm just going to state the engineering Bernoulli equation. We are using it for a utility purpose anyway. Okay, we are not looking at the basis. So, however, be assured that it can be derived from fundamental principles. So, it is definitely valid. So, the engineering Bernoulli principle states that delta P by rho plus delta V squared by 2 plus G delta Z, this much you know already, plus frictional losses per unit mass, that is FL hat, frictional losses per unit mass, plus shaft work per unit mass, WS hat is per unit mass, to indicate per unit mass, equals 0. Okay. This is the famous engineering Bernoulli equation 3.9-5 in this course book, and so on. So, FL hat is friction losses per unit mass, WS hat is shaft work per unit mass. It's nothing but shaft work divided by the mass flow rate. That's what WS hat is. Also, what we are going to do is, we are going to use something called a friction factor approach. We will determine the friction factor for different situations, and that friction factor allows us to do very many design aspects and also take care of some operation aspects. Okay, so our main aim in this particular approach would be to find the friction factor for various different situations. Okay, and you have a different friction factor for each situation. We are going to define a friction factor first. and then find the friction factor for different situations. Once we find the friction factor, then everything else falls in place. Okay? That's the way this is going to be, and that's the way the remainder of the this chapter is going to be. We are going to find friction factor for various different practical useful situations. So just to re-emphasize, for design and operation, the friction factor approach would be the easiest with an acceptable balance between rigor and ease of usability. This equation, of course, is from fundamental basis, from the momentum balance equation. So there's no difficulty with this. As to how we use this, you need the friction factor for each case. Let's start with the case that we are most familiar with, friction factor for flow through a straight horizontal pipe. Should we take a break? Yeah, why don't we take a break? You've been introduced to the turbulent flow approach, the engineering Bernoulli equation approach. I've introduced the engineering Bernoulli equation to you. And let's take a break, then we'll start the next class. We'd look at the friction factor for flow through a straight horizontal pipe. See you.